Welcome to a deep dive tailored for STEM minds like yours. Today, we're going to explore the world of color theory, a topic that you know combines physics and biology, and even a bit of psychology.
It is fascinating how something as fundamental as color, to our visual world, has such a rich history, a history of both scientific inquiry and artistic exploration.
And to trace how our understanding of color has evolved, we're going to dive into excerpts from A History of Color Theory. We'll also be looking at the Wikipedia article on color theory itself.
Yeah, we're going to go all the way from the musings of ancient philosophers to modern scientific breakthroughs.
So let's start with those ancient philosophers. We often hear about Aristotle's ideas on color. You know his belief that all colors came from black and white. Why did this idea, as simple as it sounds, hold sway for so long?
Well, I think it's partly due to the limited tools and understanding they had at the time. Without instruments to analyze light, the idea that colors come from light itself would have been hard to grasp. Aristotle's model was based on what people could see, like mixing pigments. It provided a framework that people could relate to.
Right, it makes sense. But even back then, there were challenges to this idea, right? I'm
Yeah.
thinking about those medieval scholars, like the Arab thinkers, who really started to shake things up.
Absolutely. Figures like Al-Kindi and Ibn al-Haytham, they really started to understand the role of light in color perception. Ibn al-Haytham, who is considered the father of optics, actually conducted experiments with light passing through colored glass and water, demonstrating how different materials affect the color of light. This was a major step towards understanding color as a property of light itself.
So it's not just inherent in the object, it's about the light. And then there's that discovery of multiple color paths to white. This was a real breakthrough moment by Ibn Sina, Nasir al-Din al-Tusi, and Robert Grosseteste. It seems to contradict Aristotle's single path idea.
Oh, it definitely was a significant departure. It showed that color wasn't just about adding lightness or darkness. Different colors could interact. They could interact in complex ways to create white light.
Wow.
This discovery paved the way for more nuanced theories of color mixing.
So we're seeing a foundation being laid for a more sophisticated understanding of color. And then we move into the Renaissance, with figures like Da Vinci coming into play. We always hear about his notebooks. But what about his approach to color stands out?
Well, Da Vinci's observations went beyond simply describing colors. For example, he noticed how the perceived color of an object changes based on the colors around it. He even formulated rules for painters, rules to help them create more realistic depth in their work.
That's fascinating. It sounds almost like an early form of what we now call color theory for design and user interface.
It really is. The Renaissance was a time of bridging artistic observation, bridging it with a growing scientific curiosity about the world.
And this sets the stage for the 18th century,
Mhm.
where the term color theory comes into its own. This is where we encounter Isaac Newton and his work optics. It's not just about the famous prism experiment, is it?
Oh no, it's much more. Newton argued that color wasn't inherent in objects, but it was a property of light itself. This really sparked debate because it challenged centuries of thought.
It really did. So what were some of the key criticisms of Newton's theory?
Well, some people argued that Newton focused too much on the physics of light, that he ignored how humans actually experience color. Others questioned how his theory could be applied practically, especially for artists who rely on mixing pigments and not beams of light.
Right, they're not working with pure light.
Exactly.
So it's highlighting that tension, the tension between objective measurable color and subjective perceptual qualities,
That tension is always there.
especially in art and design. But even with those criticisms, we got the RYB color model from this time, red, yellow, blue. It's still used in art education today.
Yeah, it's true that it isn't scientifically accurate to how we see color, but it's simple and practical, and that made it useful for artists.
It also laid the groundwork for later developments.
Right. We started to understand how pigments mix to create different colors.
It's fascinating how a theory can be incomplete but still have a lasting impact,
That's the nature of scientific understanding.
always evolving. So we have Newton's work, but then comes Goethe, the German poet and scientist. With his theory of colors in 1810, he seemed to challenge Newton's ideas.
Oh, he did. You see, Newton focused on the physics of light. Goethe focused on the human experience, how we perceive color, emotionally and psychologically.
It's not just science then, it's personal and even spiritual.
Exactly.
So that leads to an interesting question. How did that shift from traditional color theory to a more scientific study of color impact both sides? What happened in the late 19th century?
Well, scientists started focusing on experimentation
Yeah.
and quantitative analysis. And this led to major breakthroughs. We finally began to understand the physiological basis of color vision,
So we're moving beyond just thinking about it.
right into the realm of data and scientific instruments.
And what did those instruments in that data show?
Well, scientists like Hermann von Helmholtz and James Clerk Maxwell, they did a lot of experiments to explore how the eye perceives different wavelengths of light. And we also saw the development of new instruments, like the spectrophotometer. This allowed for precise measurements of color.
So much more accurate now.
Right, and all of that led to the establishment of the RGB model, red, green, and blue, violet.
And that's the foundation for how we understand color vision today.
It is. It links the physics of light to the biology of our visual system.
That's a huge step.
It is, and it's had a huge impact. Think about the RGB model. It's the basis for digital displays. It's used in image processing. It's even used in the development of color film.
So we can really see the impact of color science on everyday life.
Absolutely. It's a great example of scientific discoveries fueling technological innovation.
But as we move into the 20th century, the story gets even more intricate, with new discoveries and challenges emerging. So we've got this shift towards scientific understanding. But did that impact the artistic side of color theory? Did the two worlds diverge?
Not at all. There were attempts to bridge the gap. Like Ogden Rood in his book Modern Chromatics from 1879. He tried to bring artistic color theory and scientific findings together.
This sounds like a big step to make color theory accessible to everyone.
It was, and it influenced people like Albert Munsell. His Munsell Book of Color introduced a systematic way to categorize color.
Oh yeah, like hue, value, and chroma.
Exactly.
And that system is still used today.
It is. It's the basis for those color charts you see everywhere.
So that's where they come from.
It goes back to blending scientific precision with practicality.
And this was all happening while industries like printing and photography were developing.
Right.
And speaking of printing, this era saw the rise of CMY, cyan, magenta, yellow, as the primary colors. Why the switch from RYB?
Well, it has to do with how we mix colors. RYB is based on subtractive color mixing. Pigments absorbing wavelengths of light, like mixing paints.
Right. The more colors you add, the darker it gets.
Exactly. CMY is based on additive color mixing, combining colored lights to create hues.
So that's like our digital displays.
It is.
So with additive mixing, adding colors gets you closer to white. But with subtractive mixing, you're removing wavelengths.
Right.
That's a really important difference.
And to get richer blacks in printing, we add black ink to CMY.
Which gives us CMYK.
Exactly.
Cyan, magenta, yellow, and black. The industry standard.
It is.
And all of this was impacted by industrial chemistry too. The development of synthetic pigments gave us so many more colors.
Absolutely.
It's impacted art and technology.
Think about the colors we see in modern art, the colors on our screens, even the colors in printed materials. It's all thanks to chemistry.
We take it for granted. But many of those colors didn't exist a century ago.
It's true.
And on the artistic side, there's the Bauhaus movement. Artists like Kandinsky and Albers, who explored the emotional and psychological power of color.
The Bauhaus artists were really interesting. They blended intuition and scientific inquiry.
So they weren't just mixing pigments or studying physics. They wanted to understand the connection between color and the human psyche.
Right.
But how does color theory evolve from there in the face of all this new technology?
That's where color science really comes into its own. It combines physics, biology, psychology, and computer science.
To study how we see and use color.
Exactly.
That's pretty relevant for a STEM audience.
It is.
So what are some of those key advancements?
Well, a major area is the development of color space models, like CIE, XYZ, and CLAB. These models define and represent colors numerically.
So we can all be on the same page.
Right. It ensures accurate color reproduction across devices and media.
That's so important. For computer graphics, photography, and printing.
It is.
So it's like the language of color?
Exactly. And then there are advancements in color management systems, using software and hardware to ensure accurate color.
Like calibrating your monitor or printer.
Exactly. So the colors you see on screen match what you get on paper.
Wow. It's incredible how precise it's become.
It is. It's not just artistic talent anymore. It's about a deep understanding of science and technology.
And with the rise of digital media, color science has expanded even further.
Right. Now we're studying how color is perceived in virtual environments and augmented reality.
So color theory has gone beyond the physical world.
It has.
But even with all these advancements, there's still a mystery surrounding color.
Absolutely. We've made progress, but the subjective experience of color is still being explored.
It's a reminder that color is more than just data points and wavelengths.
It is.
It's part of the human experience.
It shapes how we see and interact with the world.
So where does color theory go from here? What are the next frontiers?
Well, think about fields like nanotechnology
Mm-hmm.
and new display technologies. They're changing how we create and experience color.
Those new screens are so vivid.
They are. And with nanotechnology, we can manipulate materials at the atomic level.
Wow.
Imagine colors with even more brilliance and saturation.
That would be amazing.
Or materials that can change color.
Really?
The
Huh.
possibilities are endless.
So it's not just about understanding the colors we see now, it's about creating new colors.
Exactly.
And then there's the challenge of virtual and augmented reality.
Right. How do we replicate the nuances of color in a digital space?
It's a whole new set of challenges.
It is.
Looking back on this journey, what's the key takeaway for our listeners?
Yeah.
Especially for someone with a STEM background.
I think it's important to never underestimate the power of color. It combines science, art, and technology,
It really does.
and it offers endless possibilities for innovation.
It sounds like understanding color theory can open up new avenues for STEM professionals.
It can.
It's fascinating how something as simple as color has this rich history,
It is.
a history of scientific inquiry and artistic
And
experimentation.
philosophical debate.
And as technology changes, our understanding of color will too.
It will.
So to our listeners, we encourage you to dive deeper into these topics.
There's so much to learn.
You might even find inspiration for your next STEM project.
Who knows, you could make the next big discovery.
Thanks for joining us.
It was a pleasure.
It really makes you wonder where color theory goes from here. What are the next frontiers with all this new technology?
I think nanotechnology is a big one, and the development of new types of displays.
Yeah, you see those new screens, the colors are incredible, almost hyper-real.
They are, and with nanotechnology, we're talking about manipulating materials at the atomic level, which could lead to entirely new pigments and color effects.
So we could create colors that have never been seen before.
That's right. Imagine colors with unbelievable brilliance and saturation, or even materials that change color based on their environment.
Wow, that would change everything.
It would. And then there's virtual reality and augmented reality. How do we create realistic color in those digital spaces?
It's a huge challenge.
It is.
So looking back on all of this, what's the one thing you want our listeners to take away from this deep dive?
I'd say it's to never underestimate the power and complexity of color. It's not just science. It's art and technology, too.
It really is a fascinating field.
And for those in STEM fields, understanding color theory and color science can open up new possibilities.
I think that's a great point. It's a reminder that even something as basic as color has this incredible history of scientific and artistic exploration.
It does.
And that exploration will continue as technology advances.
Absolutely.
Well, thanks for joining us on this colorful journey.
That was my pleasure.
We encourage you to learn more, and maybe you'll even make the next big discovery in color theory.
You never know.
That's it for this deep dive. Thanks for listening.